right, now let's learn how to write Lewis structures for these molecules, these covalently bonded molecules. Now, when we look at these Lewis dot structures for individual atoms, generally speaking, if there's an unpaired dot, we can pair it up with another dot and make a bond, okay? So boron actually prefers 3 bonds. Boron's interesting. It's famously electron deficient. It's actually perfectly happy simply pairing up each of those 3 unpaired electrons and having a sextet instead of a full octet. Carbon has 4 unpaired electrons. Carbon likes 4 bonds, all right? This with carbon is a pretty strong thing. Carbon likes 4 bonds, all right? It's very rare to deal with a carbon that doesn't have 4 bonds. Everything else is a little bit squishier. Nitrogen likes 3 bonds, oxygen likes 2, fluorine likes 1, but we'll see some exceptions to things like nitrogen and oxygen where we might not always have the perfect number of bonds. Okay, so we've got our bonding pairs. Those are involved in bonds. We've got our lone pairs. They're not involved in bonding. And then the bond order is the number of bonds. So is it a single bond? Is it a double bond? Is it a triple bond? Okay. So what we'll do to write a Lewis structure is first we'll count up the valence electrons. Then we will place things around each other. We will put a skeleton structure together because we don't have a molecule unless we have everything at least hooked together. Then we're going to move all the rest of the electrons around to make sure that we're satisfying the octet, or in hydrogen's case, the duet. And if our central atom doesn't work out properly, then we'll start looking at, all right, do we need to potentially have more than just a single bond? All right, hydrogen. Not nearly all compounds. All compounds, hydrogen will only form 1 bond. This is a hard and fast rule, okay? Hard and fast. This is always. Okay, hydrogen cannot form more than 1 bond. It is incapable of forming more than 1 bond. It doesn't have space for any more electrons. It only has access to that 1s orbital for bonding. Carbon is also pretty hard and fast. There's a few very rare exceptions, like say we have carbon monoxide where I just have 2 things hooked together. There's nothing higher than a triple bond, and so in that case, carbon won't have its preferred number of 4 bonds. But like 99.9% of the time, carbon's going to take 4 bonds. Nitrogen prefers 3, oxygen prefers 2. These are not hard and fast though. We can be a little bit squishier with that. And then halogens, so fluorine, chlorine, iodine, bromine, they form 1 bond when they're surrounding atoms. And fluorine, being the most electronegative element, is always a surrounding atom. So if you saw, if you were paying attention on a previous slide, okay, I said that the atom with the lowest electronegativity usually goes in the center, okay? Fluorine always has the highest electronegativity. Okay, so we're going to go through several examples here. Okay, so first thing, we're going to calculate those valence electrons. So carbon has 4. Okay, chlorine has 7, so 2 times 7. And fluorine also has 7, so 2 times 7. So we have 32 electrons in total. All right, so now I'm going to put carbon, a chlorine, a chlorine, a fluorine, a fluorine. So now I'm going to connect everything by a single bond. Single, 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 single. All right, so I have 4 single bonds. I've used up 8 electrons. So I'm going to come over and I'm going to make a ledger here. I'm going to subtract off 8 electrons. I'm going to be left with 24 electrons. And at the end of my structure, everything needs to have its octet or duet satisfied. And we have to have used exactly the number of electrons that we had. All right, now carbon there in the center, it has 4 single bonds to it. 4 single bonds to it totals 8 electrons. Carbon has an octet. It's happy. It's good. All right. So now we got to figure out chlorine and fluorine. Well, chlorine, both of them need 6 more electrons each. Fluorine, both of them also need 6 more electrons each. 24 divided by 4 gives me 6. So let's see if I do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. My ledger is 0. Everything has an octet. Okay, let's try this one right here. Okay, so I've got 4 from carbon, 1 each from 2 hydrogens, 6 from oxygen. So I have 12 electrons. Okay, so carbon, oxygen, hydrogen, hydrogen. Okay. All right, so here's my 12 electrons. All right, I do 3 bonds to that carbon. So that's 6 electrons. So I have 6 left over. Now, keep in mind, carbon absolutely needs to keep those 4 bonds unless it's something weird like carbon monoxide. So right now, carbon only has 3 bonds. It does not like lone pairs. So the most logical thing here to do is to figure out a way to give carbon another bond. Well, I can't give a double bond to either of the hydrogens. Remember, hydrogen can only have a single bond. So the only thing I can do to make sure carbon gets its octet and doesn't have to have a lone pair is to put another bond right there and put a double bond to the oxygen. That'll take away 2 more electrons. Now I'm left with 4. Okay, carbon, octet, good to go. Each hydrogen, duet, good to go. Oxygen though, my double bond there, that's 4 electrons. Oxygen needs an octet. We need 4 more electrons. 1, 2, 3, 4. Let's subtract 4 from here. All right, we've got our ledger down to 0. And oxygen has its octet. So we're good on that one. Okay. So 2 times 1 for the hydrogens plus 6 from the sulfur gives us 8. Okay, there's my skeleton framework. I've used 4 electrons. So I have 4 more left. Okay, can't put any lone pairs on hydrogen. Sulfur needs its octet. 1, 2, 3, 4. Okay, all right, let's try another one. All right, now I have 4. Okay, so I'm going to get, all right, now this one's interesting. Remember, hydrogen can only have 1 bond. So we cannot do our framework like this. Okay, this is no. Okay, and it's no because of that right there. We cannot do that. Okay, so let's erase this. Well, what could we do instead? Well, we could put the carbon and then the oxygen. That might work. And then carbon still needs 3 more, so we'll put those around it, and I'll put that there. Okay? The other way I could write this is like that. If I had written it like that, that would actually tell me that the conductivity or connectivity of this is the carbon and the oxygen and then the hydrogen surrounding it. Okay? So this tells me that I have carbon with 3 hydrogens, then the oxygen with that hydrogen. So now I've used up 2, 4, 6, 8, 10 electrons, leaving me with 4. All my hydrogens are perfectly fine. My carbon has 4 bonds around it. It's perfectly fine. What's left? Well, my oxygen has 2 bonds around it and no lone pairs yet. It doesn't have an octet. It needs 4 more electrons. So I can do 1, 2, 3, 4. All right, I'm good to go on that one. Okay, all right, so this one, we've got 2 nitrogens at 5 each, so I have 10 electrons. Nitrogen, nitrogen, that uses up 2. Okay. Well, each nitrogen needs 6 more electrons because I only have 1 bond there. I only have 8 left. So let's try another bond. That gives me 6 electrons left. Well, now each nitrogen still needs 4. I'd need 8 more electrons from that. I don't have that much. So let's try another bond. That gives me 4 electrons left. At this stage, each nitrogen only needs 2 more electrons each. 4 divided by 2 gives me 2. So there's my nitrogen. Okay. And our last one, carbon dioxide here. (16 electrons. Okay. All right. There's my framework. I've used up 4 electrons. I have 12 left. Now remember, carbon does not like lone pairs. So let's go ahead and give carbon 2 more bonds. Okay, how many more electrons does each oxygen need? Each oxygen needs 4 more electrons. 1, 2, 3, 4, 5, 6, 7, 8. Okay, all right. Now, if we are dealing with ions, we need to account for the electrons in the ion. So if it's an anion, we add electrons. If it's a cation, we subtract electrons. All right, so we'll try some examples. All right, so we have hydroxide here. Oxygen has 6 valence electrons. Hydrogen has 1. We have an anion with a -1 charge, so we're going to add 1 extra electron for 8 electrons. Okay. That's all the bonding I can do. Just so happens oxygen needs 1, 2, 3, 4, 5, 6 more to achieve its octet. Now, the last thing I'm going to do, because this is an ion, is I'm going to encase this in brackets and put the charge of the ion on the outside. Okay? Now let's try a cation. 3 hydrogens at 1 each, plus the oxygen. Now I have cation. So I need to lose electrons equal to the charge of the cation. It's a +1, so I'm going to lose 1 electron. This also has 8 electrons. All right, so we'll build our framework, our little skeleton here. Okay, single bond out to each hydrogen. It's going to use up 6 electrons. I have 2 electrons left. Oxygen still needs 2 more. Okay, and then we'll bracket this and put that plus on the outside. All right, 1 more ion. Okay, we've got sulfur at 6, 3 oxygens at 6 each, and then I have a -2 charge, so I'm going to add 2 more electrons. So we're going to get 26 electrons. All right, so there's my framework. So we'll take away 6. Okay. All right, so sulfur still needs 2 more electrons. So let's see what happens if I put a lone pair on sulfur. That gives me 18. All right, so sulfur has its octet. Now I have 18 electrons left, and I have 3 oxygens that each need, well, I have 2, 2, 2. So each oxygen needs 6 more electrons. Let's see what happens if we do this. 1, 2, 3, 4, 5, 6. I'm not sure where that weird line just came from. That was really bizarre. Okay. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Well, 6 times 3 just happens to be 18. And so we'll put our brackets, and we'll put our -2 on the outside there. Okay? Now, sometimes we can write more than one valid Lewis structure for something, And so we get what is called resonance. All that changes in resonance is where the electron density is. So we might change the location of a lone pair and a double bond. We do not change how anything is connected though. We just move around where the bonds are. What we see in reality though is what we call a resonance hybrid, where the electrons that can move around like that are actually going to delocalize. So if we have a structure where we can draw 3 different things from it, okay, like this carbonate anion, we don't see 2 carbon-oxygen single bonds and 1 carbon-oxygen double bond. What we actually see is 3 carbon-oxygen bonds that are kind of about 1 1/3 bond lengths. Okay, we can measure the length of a bond. Okay, so all 3 of these structures for that carbonate ion are completely equal. That's why we draw them with the double-headed arrow in between them. All that we did was we moved around where that double bond was. All right, so we're going to try a couple of these. All right, so ozone. I'll let you count the valence electrons and see if you can get a structure that looks like mine. All right, so that is one structure for ozone. I arbitrarily decided to place the double bond between the middle oxygen and the right oxygen. I can draw the exact same structure, but just show it over here. All right, so there's my resonance on that one. Okay. All right, so here's an anion. So I mentioned before that that oxygen and nitrogen don't have to have 2 and 3 bonds respectively. I can draw a few structures for this. So again, I want you to try counting these electrons up and see if you can get what I got here. But we can get this. We can get this, or we can get this. Okay, so we can draw 3 different structures for that resonance.